Welcome back to UBC CS 532W, Graduate Probabilistic Programming. I'm still Frank, and I hope you had a pleasant holiday weekend. Today we're going to talk about alternative variational bounds, subject near and dear to my heart. Last time we had a really cool lecture on reinforcement learning, where we talked about learning policies or controllers that maximize reward. And we said and showed that selecting actions that maximize reward can be framed as a posterior inference problem, which means that we can take all of our inference algorithms and bring them to bear on this problem. We demonstrated that FOPL language facilities are too weak to express most RL problems. And then we showed that in particular, amortized variational inference in a HOPL program is equivalent to model-free policy learning, reinforcement learning. And then we pointed out really quickly that the Markov structure of the Markov decision process is exploited in mainstream reinforcement learning algorithms. Today, we're going to talk about alternative variational bounds. And just to remind us, although I think everybody's probably up to speed on this at this point, variational inference casts inference as optimization. Okay, and we've talked about three different kinds of variational inference, really, what's going on, right? So learning a variational distribution, the first part was parameterized by lambda, and it was for one particular inference problem. So let's use variational inference to solve an inference task in a specified model with a known parameter theta. And we went off when we maximized an elbow with respect to lambda, and that drove qx given y close to p x given y for that particular model indexed by a particular value of theta. Okay. Then we said, actually, we can do model learning, right? So if we do component-wise maximization of the elbow with respect to both the model parameters theta and some variational parameter lambda, then this is basically the same thing as doing expectation maximization for maximum likelihood parameter learning in a latent variable model, or model with latent variables. And then we've looked at amortized, in particular, variational inference as well. And we did this sort of at the same time as we did meta learning because they're actually very closely related, right? So amortized inference is meta learning of the variational approximation in IID models with local latents, and is what basically that's what is what a variational autoencoder is, what a structured variational autoencoder is, and what the foundation of deep probabilistic programming is. So here, this otherwise fixed parameter lambda became a function of the data, and we learned a parameter phi, which is the amortized variational inference artifact parameters that map from the data y to the variational distribution over x. And I should be saying yn and xn here to indicate these are data and latent variables corresponding to one task. Okay. So all of these methods maximize a bound, really, on the log evidence. Okay. During the class, we've seen two alternative methods to estimate the evidence in particular. One via importance sampling and one via sequential Monte Carlo. So I should really get rid of that. So the question is, can we marry these techniques to variational inference? Okay. And please, again, I can see that that we're at the end of term desperation period, and everybody's overstressed and tired and whatever. Please ask questions as we go.
Maybe I can start us off.
Please.
There's kind of a difference between this, right? Like, because the elbow is a bound on the evidence, while the other ones are estimators of the evidence.
Yeah, great. Perfect. For the first time in the entire course, the next slide actually addresses the question at hand. It's a miracle.
Right.
So the key idea which we're going to exploit twice today is as follows. If you have an unbiased estimator, And here, this little 3 equal sign thing just means that I was too lazy to change all of the notation and all of the lecture slides to be one or the other. P hat of y given theta, that's the same thing as p hat theta of y. Okay, these are just a marginal likelihood, so it's a model indexed by theta, right? What does it mean to have an unbiased estimator in the frequentist sense? It means that in expectation, and we're going to talk about what this expectation is with respect to, this is the one thing that could potentially be confusing in this lecture, so make sure you get this part. In expectation, the idea is in expectation, the definition of unbiasedness says, okay, whatever the hell you guys are doing in the chat channels without actually making it apparent to me is I'm really missing out, because you guys are laughing your butts off and clearly there's some stuff going on in the chat channel. So stick it out there so I can see it in this chat channel rather than the Slack chat channel. Okay. Definition of unbiasedness is, of course, in expectation, the true model evidence. In expectation, the estimator is the expectation over whatever uncertainty there is in the estimator is the true marginal likelihood. Okay. When this is true, then we can just invoke Jensen's inequality and say the expectation of the log of the estimator, this is Jensen's right here, is less than or equal to the log of the estimate, the expectation of the estimator. And if the estimator is unbiased, then in expectation, the estimator equals the true marginal probability, right? Fairly straightforward. But that's pretty cool. That means that if you have an unbiased estimator, immediately you have a way of constructing a bound on the evidence.
Can I ask a question?
Yep.
Why would you go from an unbiased estimator to an estimator of a bound? Like, what's the advantage in that? It seems that you're sort of doing worse, right?
How do you figure?
I mean that you go from b hat y, which is an unbiased estimator of by, to having a bound on log by.
Mm-hmm.
If that makes any sense. Like where's the gain here?
Is this going to happen twice? Let me see. Hold on. Okay. 2 times. 2 times in a term is better than 0 times. So note, I do want to just draw your attention to this again. Note that the expectation here is over the sampling distribution of the estimator, okay? Right? In other words, how the estimate itself varies, right? So there's going to be random variables consumed in constructing the estimate, right? How does that estimate vary? Okay. I think it's going to be 3 slides before this kicks in, maybe 4. But for the moment, let's remember self-normalized importance sampling from lecture 4-5. Everybody will have, it's certainly important sampling at this point will have come across, right? So we have our posterior distribution. We want to compute some expectation with respect to it. We can't do that. We use a proposal distribution Q, right? But we can't evaluate the posterior distribution, so we stick the joint in there. The marginal probability comes out here, right? So this is just, important sampling, but we have this self-normalization problem, which is we have to estimate p theta y. And the way we did that was that we just made r of x 1. And then if you just look at what this expectation is, this is an estimator for the marginal likelihood or the evidence, right? That's, of course, what we do. We just basically compute the average of the weights. And that's an estimate of the marginal probability or evidence. In other words, what we've defined here is, and this is again is just definition of some notation that we use, P self-normalized importance sampling, hat of y, is just p hat theta of y. So we're computing the evidence of the model under parameter theta here, right? It's just the average weight under some importance distribution q phi, right? Right. And we claimed, and we gave a kind of a hacky proof before, that p hat theta y, this thing, is an unbiased estimate of the marginal likelihood. Okay? In other words, exactly the condition that we talked about before holds. In expectation over whatever sampling procedure, p hat y is equal to p hat theta y. Our estimate of the evidence is unbiased, which means that it's in expectation the true marginal likelihood. So this is true, but this perspective and the way we did it before obfuscates the frequentist sampling distribution of this estimator, right? In actual fact, the sampling distribution of the estimators with respect to the joint distribution of all k samples from q phi. Okay, so the notes provide a nice derivation of this, and we'll hit the key points. And the key point, without any question, is this, right? So this estimator, how it varies, its sampling distribution is a function of the joint distribution of all of the random variables generated when constructing that estimate, right? So the joint distribution of all the random variables used to construct that estimate are the k samples from Q. So every time you change one of those samples from Q, your estimator changes. So it's pretty clear that it's the value of the estimator is dependent on that, right? So, you know, we have this distribution of Qs, right? The definition of our estimator is, we just plug that in, right? We use the linearity of expectation to pull the expectation inside. And note this product is over I and the sum is over J, and we're just being very, very careful here, right? And then all of these are independent. So when I equals J, then you get a term, and then all the other things in that particular product integrate to 1. This is a little bit quick, but you can look at the notes. It's pretty straightforward. Because at the end of the day, what you get is basically a sum over K of the marginalization of the joint over X, which is just a sum over K. It's just the average of the evidence, which is just the evidence. So in expectation, so this is a proof, very fast proof, that in expectation, the P hat SNIS estimator is unbiased.
Can I ask a question?
Please, thank you.
I can't seem to figure out where we define P theta y. Is that just like a quantity we're trying to learn or find out what it is?
So P theta y, this thing?
Yeah, yeah.
I mean, P theta y is this evil thing called the evidence that we keep messing around with, right? So P theta y is, there's a whole bunch of ways to get at it, right? It's P theta xy dx, or more importantly, P theta of x given y is P theta xy over P theta y, okay? And when we're doing variational inference, if you remember, our goal has always been to maximize a lower bound on this quantity, a number, the evidence lower bound, right? So when we're doing that, just to be 100% clear about this, right? Right. When we maximize the elbow is evidence lower bound, right? And when we maximize the elbow, we do two things. One, we increase our approximation of the evidence. But more importantly, the way the bound is constructed, we drive the KL divergence between this and this to be small. That's the simultaneous action of this variational inference thing, right? When we do model learning, we also want to increase the evidence lower bound, because that will assign more probability mass to our observations.
Could Could you remind me the elbow, we're trying to maximize it as a function of what variable? Because I'm just a little confused with the different variables.
Yeah, so this is, so in general, there's three. We did three different versions of it. The first bound was with respect to just lambda. So we're trying to learn a variational approximation to a posterior in a problem. Then we talked about model learning when we maximized the elbow with respect to theta and lambda, which was a way to increase the marginal likelihood of the data, which is the maximum likelihood component. And we simultaneously, in lockstep, maximized the bound with respect to lambda in order to basically help learn the model. And then when we did amortized inference, we optimized the bound with respect to phi and theta, which gave us amortized inference, an amortized inference artifact that gave us a rapid approximation to the posterior, and also gave us a good model of the datum yn, averaged across all data.
So why is it that the theta is a subscript? It's like fixed now in our setting?
No. I think they're the same. It's just it's notation.
Okay, so they're the same for the estimator and for the actual like P without the hat.
Yeah.
Because here you have it for both.
Yeah, it's just notation. Either it's semicolon theta or theta under in the bottom. Both are equivalent notation for it's a parameter. We're treating it as a parameter. We're going to compute a point estimate.
Is it what I get from that notation is that it's like fixed. That's the way is it fixed or is it not fixed?
It's definitely not.
Okay.
It's something that we're going to learn. It is going to be a fixed quantity at the end of the day after we optimize it.
Okay.
But during optimization, we're definitely going to be changing its value.
Okay.
Right. Okay. So let's just link this together again, just really quickly, and say it again, right? So we have this El Nito thing, which is if you have an unbiased estimator, then straight away you can use that unbiased estimator to be an evidence lower bound, or a log evidence lower bound. Fine. Okay. And importance sampling isn't what all we've established at this point is that importance, the normalization constant estimate, the average weight from self-normalized importance sampling is an unbiased estimator of the marginal likelihood. Okay. That means that we can use the evidence estimate from self-normalized importance sampling as a lower bound that we can use to do model learning, amortized inference, variational inference, you name it. And the first of these that we're going to talk about is the importance weighted autoencoder, right? Which, despite its name, is not actually an architecture, but is instead a variational objective. And this is IWay in one slide. So IWay exploits the unbiasedness property of the self-normalized importance sampling marginal probability estimator. So this is what we've just been talking about and established that it's unbiased, P hat SNIS of Y, right? And defines a bound for a particular data set as just being the expectation over a bunch of important samples of the normalization constant estimate arising from self-normalized importance sampling. So here's the normalization constant estimate, right? That's P hat SNIS theta. We could put theta here if we want. It's all theta's everywhere, right? And the expectation is taken with respect to a bunch of samples.
Can I ask a quick question here?
Yep.
Is the only difference with normal elbows just that you're taking more samples?
Well, I mean, normal elbow is okay. If K is 1,
Yeah.
this clearly reduces to the normal elbow.
Yeah, okay, sorry. Yeah, that's what I meant to ask. That's
right.
a more clear.
So if you get rid of this, that's the elbow.
Yeah.
Right.
Yeah.
So now this is getting to your point. So what is the point, right? So if we let L subscript little k be the I-way loss that we just described with little k samples, so in other words, you know, the product is to little k, the sum is to little k, you divide by little k, so on and so forth. The original I-way paper and the notes both show that I-way bounds the marginal likelihood more tightly than the evidence lower bound. And this is not terribly surprising, right? If you use more samples than 1 in order to get an estimate of the marginal probability, chances are your estimate is going to be better, right? So it's not terribly surprising, right? So they proved a stronger result, which is that this I-way bound for, so LM is less than LK for M less than K. So if you use a smaller number of samples, then the bound is less tight. If you use more samples, the bound is more tight. And as Baron pointed out, with K equals 1, the I-way reduces immediately to the elbow. And this implies that elbow is a lower bound on I-way is a lower bound on log p theta y. Okay. And this proof shows up in the lecture notes with a little bit of additional commentary, right? It's also not unreasonable to note that this is basically, this outer thing is an average, so there's a strong law of large numbers kind of result applies straight away, right? So as k goes to infinity, it's also demonstrated in the paper that LK goes to the true log evidence. So arguably the most important thing that you'll get out of hearing about what I-way is that for this reason, I-way is used very frequently to evaluate models, in particular by just using a very, very large number of samples and evaluating the I-way bound and using that as a stand-in for the evidence, right? A tight bound on the evidence. And that's regardless of the loss that you use to train the model, however you get to it, to evaluate and compare two models, you just run I-way to compute an evidence, which is basically a likelihood. Everybody likes to compare models via likelihood.
Can I ask another question?
Yep.
Maybe actually I'm really looking at the slide, might actually be on here, but does the, oh yeah, sorry, I see it on the slide now. I was going to ask whether if you take infinitely many samples of I-way that you actually approach the true evidence, but I see that now. Sorry.
Yeah. Yeah. So cool. So now the answer to Baron's question, which I guess took six slides rather than 3, is that now there's a deeper question. It's a little bit complicated, right? So why would bounding the likelihood or the marginal likelihood or the evidence be better, right? And this is a very complicated question that involves like basically the optimization paths that come out of these different algorithms and all sorts of stuff. And it's not entirely clear that the answer is completely sorted at this point, right? But frequently it has been demonstrated that the models that you learn under the I-way end up arriving at higher evidence estimates. In other words, they end up even within the same model family at parameter values theta that have higher evidence values, which means that they're basically in the maximum likelihood framework, better models. You've actually maximized the likelihood of the data under your model better. Unfortunately, there are some caveats. So one big one is that training under the I-way loss effectively always makes your inference network, particularly in the amortized inference setting, worse. And we'll talk a little bit about why that's true. And the other bit is that the qualitative difference between models with different elbows is not always hyper evident, right? And if you're going to choose a thing to work on, probably architecture choice or probabilistic program, the program itself is probably more important than the loss. But here's an example, right? So this is a continuous VAE model trained using 3 different objectives. We'll talk about, we've already talked about VAE, which is in our case actually just the elbow. We're talking about I-way now, and we'll talk about TVO in a little bit. This continuous latent variable model, a VAE basically. We've talked about what these are for MNIST already as well. This is really P of Y in what we've just been talking about. And what you should see straight away is that the log evidence here, which is a proxy for how good the model is, the lines in green, you can just look at the solid lines. That's the number of samples that are used, right? There's different ways of using samples, but in the elbow, a 50 sample bound results in a model with learned evidence here, and with I-way, the I-way loss, you learn a significantly better model in the same number of epochs, basically the same amount of compute. Okay. Questions? We'll come back to this when we talk about TVO. Yeah. Okay. What other way of estimating the marginal probability have we seen in class? Don't everybody shout out the answer at once. It's overwhelming.
SMC.
Oh, I think you and Vasilios tied, one by voice, one without voice. All right. Yes. So going to Monte Carlo. Okay. So we did Sequential Monte Carlo. Here's a slightly different notation. It's really the same. You remember what's going on in sequential Monte Carlo. We have some observed values. We've got model parameters, proposal parameters. We have a proposal distribution Q, which is parameterized by phi. And we go stepwise through basically a state space model, and we frame probabilistic programs, particularly in the Hoppel context, as state space models, where the state transition is pretty complicated, right? You compute some set of weights at the first time step, which is just the prior over x times the likelihood divided by the proposal. You get the average weight, and you initialize the particle set. And then for every resampling step, as you go along, you sample an ancestor from the distribution parameterized by the average weights. You sample a particle value from the ancestors from the proposal distribution. You update the particle set, and then you compute the weights and compute the average weight, and compute and then you cycle through, keeping track of the unnormalized weights and whatever. You already know how to do this because you did the homework, and then you compute the marginal probability estimate as the product over all of the resampling steps of the average weights at those steps. So at the end of SMC, you get a set of particles, you get a set of weights, and a marginal likelihood estimate. Cool. That's pretty cool, right? Okay. So, and in the sequential Monte Carlo lecture, we showed that multiplying the average unnormalized weights at each sampling point results in a marginal probability estimate. That's the critical thing that we need to remember, right? And we asserted, and I'm not going to prove in lecture today because it's a hideous, hideous, hideous proof, right? We asserted that the marginal probability estimate from sequential Monte Carlo is unbiased, right? And you can get proofs for this in various places. My former student's PhD thesis is one nice reference for it, if you care to consume the proof. But if you believe it, which there's plenty of reason to believe it because it's true, right? Basically, if you take this and you believe that it's an unbiased estimate, then from the very beginning, we know how to build a bound on the log marginal probability, right? The log evidence, right? So this gave rise to basically 3 papers that came out at the same time. Complicated political reasons for that, but AESMC were what came out of my group, and then also 5.0 and Variational Sequential Monte Carlo basically all came out at the same time. And it all comes down to saying, okay, there is this unbiased estimate of the log marginal, of the marginal probability estimate that comes out of SMC. So we can construct a bound on the log evidence by taking an expectation with respect to the sampling distribution of the SMC marginal probability estimate. And this is where things get a little bit hairy. You can imagine why the proof of the unbiasedness of sequential Monte Carlo is a little bit hairy, which is that this expectation, in other words, the randomness in the sequential Monte Carlo evidence approximation takes into account all of the randomness consumed by sequential Monte Carlo, right? And we talked a little bit about this in the sequential Monte Carlo lecture. I'm guessing that these statements about all of the randomness in sequential Monte Carlo maybe passed some of you by, maybe all of you, maybe even me. But QSMC here is, of course, clearly for all k particles, the latent state value for all k particles, right? And this, I suppose, technically should be 1 here, times the proposal of the latent state given its ancestors at all time steps for all particles. So this is the product over k and product over t, times the discrete distribution from which you drew the ancestors according to the calculated weights. So the frequentist sampling distribution of the SMC estimate is distributed according to this proposal, the full SMC proposal mechanism. Make sense? Okay. But this is fine because we know that this is a bound, right? And that means for the same argument that we used for the importance weighted autoencoder, we can say that AASMC, as we just described, is the expectation over the frequentist distribution of the log marginal estimate from SMC, or the marginal probability estimate from SMC, is bounds the log of this, which is unbiased. So we know that this is a bound on the log marginal probability, right? So in other words, SMC, or in particular autoencoding sequential Monte Carlo, also computes an evidence lower bound that can be used for simultaneous model and inference network learning, right? Okay. So notice that the Q in here is parameterized by phi, and of course the model is parameterized by theta, right? So this now is an objective that we could target for joint optimization with respect to theta and phi. Anybody see any problem with that? It should be apparent on this slide.
It's hard to take a gradient with respect to that expectation, isn't it?
Yeah, so exactly. So if you take a gradient with respect to this Q, just like in reinforcement learning, right, we have a bunch of discrete choices here, which means that we cannot actually take a gradient through this without putting in all sorts of reinforced terms. So at the very best, we would have all kinds of very high variance gradients, so on and so forth. So what did we all do? I don't know if I even say this. I may have even skipped saying this. Yeah. What did we all do? We just skipped that part of the gradient computation. Okay. So we basically said those reinforced terms are too complicated. They're too high variance, so we're just not even going to compute them. And it turns out that this still works incredibly well. Okay. So for models in which there is a time dependency and there are partial rewards, just like before, the evidence
Can I ask a question?
yeah.
So if you just don't take the derivative and don't include those terms, how does it not accrue like a really large error?
So it comes down to, if you're solving an optimization problem, would you rather have an incredibly high variance gradient, or would you rather have a gradient that is highly correlated with the true gradient, but is in general slightly biased?
I feel like that's a non-question and I'm not entirely sure how it relates. Like slightly biased away from what it should be?
Yeah, so it might not point to the exact optima, right? But it's going to, generally speaking, point in the right direction.
So is it like
It's a bias variance.
like a lower bound, or?
So it's a bias variance trade-off. So if you have an incredibly high variance gradient, you're totally screwed. You're never going to make progress, right? But if you're willing to incur a little bit of bias in order to get rid of the variance, you're going to make progress and you're going to get close to the optima quickly.
Okay.
Right. Now, the corollary to your question is, how in whatever's name would you expect that the models that you learn using a biased gradient would still end up being any good? Right. This is a more complicated question, and I don't have a good answer for that, except that it works. So why does stochastic gradient descent in a billion dimensional space work? Nobody really knows, right? So there's this task. So here we learned a variational RNN model for a stochastically moving occluded ball. Okay, so the data, ground truth data, looks like this with different angles, different speeds of the ball, different amounts of noise, so on and so forth. So basically, there's a yellow ball that moves behind this thing, and the objective of the model is to actually generate beyond time 19 continuations of the trajectory. So we want to do model learning, right? And we're going to get evidence in the form of observations at every time step up to 19, and then we're going to unroll under this model. Should be familiar to to some people here for sure, as a general model family. Okay, so in this we have what it looks like when you train a model using iWay. What just happened? I have no idea how that worked. It would be cool if I did. If you train the model using iWay, you get basically a model that is not very performant, actually. So it doesn't do a good job of predicting where the ball will be, so on and so forth. On the right, we use AESMC, and we get a very diverse set of sample trajectories, which is lovely. And this shows up in terms of the model evidence. So here we have AESMC, so we're using the SMC bound on the marginal probability, right? Training using that, and you see a couple of things. One is that the learned models in general are better at the end, no matter how many samples you use, although not substantially in the high number of samples regime. But more importantly, in terms of how fast you learn amazingly quickly in the sequential Monte Carlo setting. Right? So, cool. Questions about this? Okay. There are some caveats, right? So I guess I do say it here. So QSMC, the empirical sampling distribution of the SMC estimator, high will by the way, requires reinforced gradient estimates because of the discrete ancestor indices sampled during resampling. Those gradient estimates are very high variance. So basically in all of the three pieces of work, the reinforced gradient terms were dropped. So that gives you biased gradient estimates, but lower variance, faster learning, better evidence, so on and so forth. And a recent result, which I've known about for a little while, but we just recently went over in my group, it turns out that there is now a fully differentiable version of sequential Monte Carlo, largely inspired by this resampling problem and the discreteness of the AKs, the ancestor indices that uses a bunch of stuff: the implicit function theorem, Sinkhorn algorithm, optimal transport to derive a fully differentiable SMC variant. This technique is pretty cool for things like reinforcement learning and the VRNN model that we had in the last I showed on the last slide. But it does require you to be able to take weighted averages of basically over path space, which is a little bit uncomfortable in the general purpose Prob Prog setting because you can't do that in general. So the problem is still there. They've just pushed it off to some other part of the problem domain. So I think this is a good place for an actually well-timed break for a change. But let's take a little pause here and just recap what we've done here, right? So iWay is a multi-sample evidence lower bound based on self-normalized importance sampling, right? So the key idea here is we're just using the importance sampling estimate of the marginal probability or the evidence. That's unbiased. We actually showed that today in class, right? This is just Jensen's in the general case, and the unbiasedness says that it's that in expectation it's the true marginal probability estimate. So iWay is a lower bound on log PY. Go do your favorite model learning, inference network learning, so on and so forth under a multi-sample objective. Right? Or evaluate your model using a very, very large number of samples from pretty much any inference network. It doesn't really matter. AESMC is a multi-sample evidence lower bound based on sequential Monte Carlo. So all this stuff we've been talking about, it's all part and parcel of the same thing. We can mix, match, and do everything we want together. So we talked about variational inference, we talked about sampling, we talked about whatever. So now we have a general method which can, encompasses important sampling, sequential Monte Carlo, and variational inference all at the same time, right? So AESMC is a multi-sample evidence lower bound based on sequential Monte Carlo. We have the unbiasedness of the sequential Monte Carlo evidence approximation. So that's this here. We have Jensen's. That's this here. So that means AESMC is a lower bound on the log evidence. Operating with AESMC until fully differentiable sequential Monte Carlo requires overlooking gradient terms, but still, even still, and this is, thank you for pointing this out, Emma, is actually kind of intellectually fascinating that this is true, still results in superior model learning when partial observations or rewards are available. And just like I-way reduces to the elbow in the single sample case, if there are no resampling steps, in sequential Monte Carlo, if you choose not to resample, then AESMC reduces to I-way, reduces to important sampling. Okay? So it remains an open question. Actually, nobody's actually demonstrated this yet, whether or not AESMC is in general a tighter bound on the evidence than I-way. But again, based on sort of our understanding of what sequential Monte Carlo does and how it works, certainly in models that have this kind of temporal structure, one would expect it to be a better bound, but nobody's demonstrated this in general. Sorry, I lied. I do want to do this slide before we take a pause. In the most dangerously titled paper to come out of my group probably ever, tighter bounds are not necessarily better. My former student Tom Rainforth pointed out a huge caveat to all of this. Although it started in AESMC where we really noticed this, 11 is AESMC. So tighter evidence bounds do result in better evidence approximation at each value of theta, better theta gradient estimates in general, and better final parameter values in terms of marginal probability. But and this is the key idea in a very technically complicated paper. In the limit of many samples, the inference network becomes irrelevant, right? So if you think about it, right, one way of thinking about it is in important sampling, if you draw enough samples from even a crappy proposal, you're still going to get good marginal probability estimates. You're going to still get good expectation computation, so on and so forth, simply by virtue of the fact that you draw an infinite number of samples, and effectively, eventually, under the conditions of important sampling, you're going to cover the space with an infinite number of samples, regardless of how they're distributed, right? Roughly, the thinking goes that the variance of a k-sample important sample Monte Carlo estimate goes down or basically as 1 over k, right? So with large numbers of samples k, our estimator goes to the true value, and p hat becomes independent then of the proposal mechanism. That's basically what I just said. And if the quantity that you're taking a gradient with respect to is independent of the parameter that you're taking a gradient with respect to, then the gradient just goes to 0. So there's a very technical argument for that in this tighter bounds are not necessarily a better paper, but the kicker is that if you're going to do multi-sample, if you're going to compute multi-sample bounds, you have to be very, very careful about what you do with your inference network, because you're going to learn a bad inference network, basically. So this ends up being a strong justification for using some of the other things that we talked about earlier in the course, like reweighted wake sleep, with I-way or SMC for learning the model parameters theta, and for instance, a wake phase sleep update for learning the inference network parameters, where you don't have this signal to noise problem with the gradient. So I think this is a good time for a pause. It's a perfect time for a pause. Let's reconvene at 4:30, 4:29. And most of us are back. Hi, Namrata. Ryan, lovely. Okay. So one more cool variational objective. So we just did IWay and ASMC and variational SMC and filtering variational objectives. These collectively have started to be referred to as Monte Carlo objectives. They rely first on forming an unbiased positive estimate of the evidence and then take the log. Another approach is to actually estimate the log of the evidence directly. And this is work that was done here in my group by Vaden Nasrani, who took this course a couple of years ago. And this was basically his project and turned into a pretty widely appreciated bit of work, such as the approach of the TVO, the thermodynamic variational objective, which estimates log p theta of y using thermodynamic integration, a method that has its home in statistical physics and in probabilistic statistical estimation. Okay. All right, so hang on to your pants here. This is a slightly different thing that we're going to do. It's not too bad. But here's the deal. The TVO makes use of a geometric path. And what do we mean by geometric path? We really just mean this. So we're going to take some scalar parameter beta, and we're going to move it between 0 and 1. Okay? And all that we're going to do for the time being is we're going to establish we're going to do some cool algebra, right? But at the end of the day, it's going to mean that we can use a scalar integral to bound the evidence, okay? And scalar integrals we can do. We don't have to do Monte Carlo for that. We can do, trapezoidal approximations or whatever, right? We can do numerical integration. Okay? So we're going to make use of a geometric path between some variational distribution q phi x given y, like usual, and our joint distribution, p of theta, y, and x. So this is our probabilistic program. This is our variational approximation, right? And we're going to make a sequence of distributions, a continuum, a scalar parameterized continuum or path of distributions, which we're going to call pi beta of x given y. So this is going to be a sequence of posterior distributions, but whatever, everything is conditioned on y. It's just some path, sequence of distributions, where pi tilde beta is going to be some unnormalized form, and there's going to be some normalization constant z of beta, okay, which is literally just the integral of p tilde of beta, whatever that is, okay, over x. So here's what p tilde of beta of x and y is. It is the joint raised to the power of beta times the posterior q phi of x given y raised to the power of 1 minus beta. So something that's really obvious, right? If you set beta equal to 1, then this path, this pi tilde path, ends in the joint distribution. If you set beta equal to 0, then this pi tilde beta path ends in the variational posterior distribution of x given y. Okay, so we usually think about things starting from 0 and going to 1. So you can think of this path as going from this variational distribution q phi x given y and going to p y given x. Okay? And this is going to be important to remember on subsequent slides. Both of these normalization constants are interesting. And this is where this is critical to understanding this technique. Really, it's just kind of algebra up to a point, very interesting algebra up to a point. But z naught, so in other words, z at the value of beta equal to 0 is the integral of pi tilde 0 yx, but pi tilde 0 is just the variational posterior, and integrating that over its x domain is just 1. So z0 is 1. So z at the beginning of the path is 1, the normalization constant. The normalization constant of pi tilde 1 is, when you plug in 1 here, the integral of the joint over x, which is our favorite thing, without any question. The central object of question from the, hello, Andres, you're also seeing, joining to see how this is going, is the model evidence. Okay. Cool. All right. So just keep that in mind. Okay. So if we take 8, 9, and I guess 11, right? Then pi 1 without a tilde is pi tilde of 1 divided by the normalization constant. Pi tilde of 1 is just the joint divided by the normalization constant. So pi 1 of x given y is just the posterior distribution of x given y. So as beta in this path moves from 0 to 1, the unnormalized density p tilde beta of y and x anneals between the variational posterior and the joint, while the normalize anneals between the variational posterior and the model posterior. So if we go back to equation 8, I'm not going to do out the algebra. Basically, if you combine 8 and 9, you stick this in here. So 8 can be straightforwardly algebraically transformed into an exponential family distribution form. And we didn't go through exponential families, but I expect that either you can get familiar with them if you're interested, or whatever. That there's only 2 facts about exponential families that we're going to use here, and I'm going to use them with citation. And again, the lecture notes have this stuff in it, so please look at the lecture notes. So we can transform. We can straightforwardly transform 8. I'll go back again just to look at it. We can transform this into an exponential family form, where basically pi beta of x given y looks like this. Okay. So there's a log partition function. So this is z of beta. We were looking at that before, right? This is just the normalization constant. X of log of that means that it's just going to come out minus, so that's going to be a normalization constant. This q goes in here, and you can see how there's a beta here and then a 1 minus beta down here, and basically it's what we had before. Okay, so looking at it this way, which Rob Breckelman's just discovered for us, is very nice because we can look at this geometric path and the construction that Vaden put together in terms of the TVO as an exponential family distribution. And this allows us to get a couple of things out that are pretty cool. So the first thing that we get out is that for any member of an exponential family, the first derivative of the log partition function is equal to the expected sufficient statistic. Okay? This is something that you just, like, either you know from exponential families or you don't, and you can go demonstrate it yourself. But the gradient of log z is the expectation under pi beta of this ratio. Okay, so you can just look this up for exponential families. This is something you just look up and know. Okay, fine. When we know this, then we can derive the thermodynamic integration identity. And this uses basically the fundamental theorem of calculus. So we say, you know, what is the antiderivative of the derivative of the log partition function? Well, that's log of z minus 1 minus log of z0. This is the fundamental theorem of calculus right here. But I told you to remember what log of z0 is. That's log of 1. Log of z1 is the evidence, so we have the log evidence here, right? And from the exponential family form of this thermodynamic variational objective, right? We get that the gradient of the log evidence is the expectation under pi beta of this ratio. And this ratio should look very, very, very familiar to you, right? This is the same ratio that we've been looking at all along. So there's the joint over the variational distribution, right? And this gives us what we call the thermodynamic variational identity. Right? So this quantity, which we're always trying to operate on and we would like to maximize for model learning, right, is equal to the scalar integral from beta equals 0 to 1 of the expectation under pi beta, right? And we defined pi beta before, of the ratio that we're familiar with the log score, or the log importance weight, basically. So that says that the log evidence can be expressed as a one-dimensional integral of the unit interval, the integral over the unit interval. And there's one other property of the exponential family, which is critical to what we're going to do here, which is that the log partition function is convex, meaning its first derivative, the integrand, is monotonically increasing. Okay, so this thing is monotonically increasing, which is cool because this allows us to lower bound the log evidence using a finite sum left Riemann approximation to this integral. Okay, so these are the equations, but I'm going to flip to here. And this picture, I think, makes a lot of sense. Okay? So on the vertical axis here is this expectation, okay, indexed by the value of beta. Okay? So if you remember that when we set beta equal to 0, right? When we set beta equal to 0, pi beta was the variational posterior. So pi 0 is q phi of x given y. Okay? That means that at 0, the value of this function is equal to the elbow. Right? Which means that if you multiply the elbow by 1, that is the area of this box. Right? But because we know from the exponential family that this function, as a function of beta, is monotonically increasing, we can construct a left Riemann approximation to the scalar integral, which is this thing. And estimating the area of that will lead to a tighter bound on the evidence. Okay. Which, if somehow we were able to integrate exactly this quantity over the range, is the evidence. Okay, so we can go back and stare at these for a little while, right, if you want to. But basically what this says is we're going to divide up beta into k different boxes, right? And then for each value of beta, we're going to estimate the area under the integral by the difference between those two times the height at either the right or the left side. Right? The left says we're going to use this value for this region. Use this value for this region. And we sum up all of these rectangles, and that is our bound on the model evidence. Okay. Oops, sorry. All right. Interestingly, in this framework, and maybe of relevance to one of the final project groups, we can also form an upper bound on the evidence, which would allow us to assert conservative estimates of a probability, right? Which is the exact same, except you use the rightmost corner, and we don't have it in this plot right here, but it's pretty clear that if you instead, oh my goodness, that's way too large. Sorry about that. If you instead used this value, the resulting integral approximation would be an upper bound. And that's all that this TVOU stands for here. So there's an upper bound to the evidence and a lower bound to the evidence, so we can sandwich the marginal probability estimate between these two bounds. Okay? And that's what we say here. Okay? So the trick is we have expectations under a bunch of pi betas now, right? And I'm not going to go into the details. It's again in the lecture notes if you want to, but the expectations under this sequence of pi betas can be approximated using importance sampling or in fact sequential Monte Carlo or whatever you want, okay? And gradients of the TVO can be computed using reinforcer or the reparameterization trick, whichever you like. Okay. The critical part is that there is this mathematical construct, which is the thermodynamic variational objective, but you can either upper bound or lower bound the marginal probability estimate. And then the question is really just reduces to how do we estimate each of these expectations? And you can do this again in many different ways. Traditional methods involve running very long Markov chains for each of these pi betas. What makes the thermodynamic variational objective slightly different is that we used a single set of importance samples and then reweight those samples according to this ladder of expectations.
Can I ask a quick question about that?
Please.
Does that basically mean that you're sort of doing sequential Monte Carlo in the betas? So like every new beta, you sort of like reweight your samples and adjust it a little bit depending on the distribution. Is that what's happening?
So that paper has not been written, but importance sampling has.
Okay.
So yeah, the issue is that you don't get more evidence, like you don't get more data as you go, right?
Mm-hmm.
So it's not clear that sequential Monte Carlo is necessarily going to help, but importance sampling can work here.
Okay.
Okay. Cool. What's kind of cool is that maybe at the very end, what we're getting close to the end of today, right? Maybe for us, the TVO's biggest utility is to provide a lens through which sense can be made of the zoo of all of these variational inference techniques that we've talked about throughout the entire course, right? From the latter third of the course. So in other words, a number of the objectives that we've talked about can be recovered from the TVO by either using a single partition or whatever. All of these methods, these are paper possibilities if you want to make new papers, can be extended by setting k greater than 1, right? So in the TVO, we have 3 degrees of freedom. We can either optimize theta, phi, or both. We can maximize TVO-L to lower bound the evidence, or we can minimize TVO-upper to decrease the upper bound, again, to sandwich the evidence. And we can either use data sampled from the true data generating distribution, as in real data samples, or we can get data from our generative model, as in the case of inference compilation. So what do I mean? So variational inference, which we talked about, can be seen as a specialization, as sort of obvious, of the TVO that learns only phi and maximizes TVO-L with only two betas, beta 0 and beta 1, right? Beta 0 equals 0, beta 1 equals 1, right? And we've already actually showed this. So the TVO with beta equals 0 is equal to an expectation over pi 0, which is just an expectation with respect to the variational distribution, q phi x given y, of the log importance weights. This is just the elbow. So argmax TVO lower bound with respect to phi with just two betas, beta 0 equals 0, beta 1 equals 1, is straight variational inference. Inference compilation is pretty cool. Again, we can look at, and this is somewhat surprising actually, if you minimize the TVO upper bound, so something that we didn't talk about in the inference compilation case is that actually that bound is an upper bound on the model evidence, right? So minimizing TVO upper bound, phi, with only two betas, beta 0 equals 0 and beta 1 equals 1, we recover the inference compilation objective. So we want to minimize an expectation over y drawn from our model of the TVO upper bound. Right? When we plug in the values of beta and the corresponding bound, if you remember, beta 1 equals 1, that was the posterior distribution. That's actually beta 1. That's the true posterior distribution. Well, if you look at this is exactly what we did before, right? So this is just, you combine these two. This is the joint distribution. Now we're minimizing with respect to theta this quantity, right? And the only terms that we have are x, y drawn from the joint distribution of our model and the inference network conditional distribution, or the variational distribution, whatever. So what we're doing when we're doing inference compilation is actually minimizing an upper bound on the marginal probability.
Is it that you have is it the sort of opposite KL that gives rise to that? Is that why?
Well, remember when we did the inference compilation thing, we used the opposite KL, but we also averaged over all of over data drawn from the model, right?
Oh, okay.
So yes, opposite KL, modeled, data drawn from the model. But it turns out that this is the same as minimizing an upper bound on the marginal probability, which is kind of interesting.
Yeah.
Right. VAE style amortized inference from the TVO perspective, right? The loss for the VA, basically it derives from the TVO perspective on the variational inference objective, except now we learn both theta and phi and average over data items drawn from the true data distribution, right? So if you do the TVO, if you maximize the TVO lower bound for a particular yi drawn from the true data distribution, then this is the same as optimizing the average elbow averaged over a bunch of data items. Okay? So this is what we did when we did amortized inference. This is the variational objective for the variational autoencoder, so on and so forth. And I won't belabor the point, but you can get to wake sleep and reweighted wake sleep from the same perspective, right? So one thing that I would encourage you to do if you end up doing work that involves amortized inference and these sorts of things, and you need to remember how they're all related to one another, the TVO gives you a nice framework for thinking about them. Okay, so pause and recap. IWay, ASMC, and the TVO are all alternative variational methods with enhanced model learning capabilities. So basically the models that you get out of these methods are generally speaking better than doing model learning under the elbow. And the TVO provides a unifying mathematical framework for understanding all of the variational inference, amortized inference compilations. You can think of them as basically different parameterizations of the TVO that form these scalar integral approximations with different numbers of bins and upper and lower bounds and these sorts of things. Okay. Cool. We've done it, almost. And the happy expressions on everybody's faces shows how happy we all are to have gone through this together. It's amazing. The outpouring of positive emotions is just almost overwhelming. But we've gone through a lot together, and we've learned an absolute ton. So thank you very much. Right. So what have we covered? Let's think back on all of the awesomeness we've done together. Right. Graphical models, Markov chain Monte Carlo theory, by hand, inference algorithm design and implementation, programming languages, programming language interpreter design and implementation, graphical model inference algorithms, first order PPL interpreter algorithms, evaluation-based inference algorithms, higher order probabilistic programming interpreter implementation, expectation maximization, variational inference, model learning, deep probabilistic programming language design, sequential Monte Carlo, amortized inference, RL as inference, and now alternative variational bounds. Right? Along the way, you have sort of magically done inference in a crazy number of models, right? Latent Dirichlet allocation, Bayes nets, Bayesian Gaussian mixture models, linear dynamical systems, Bayesian neural networks, hidden Markov models, Bayesian linear regression models, rejection sampling-based generative models, right? And you know how to write, using the Hopl in particular, or Hopl-like language characteristics, generic versions of every single one of these models that can be applied to any data, right? That's extremely powerful. Along the way, you've mastered a ton of crazy inference techniques and algorithms, enumeration-based inference, Metropolis Hastings, Gibbs, Metropolis within Gibbs, Hamiltonian Monte Carlo, black box variational inference, importance sampling, self-normalized importance sampling, sequential Monte Carlo, amortized variational inference. And we've exposed you to some crazy, crazy stuff like, actual compilers. Although you didn't have to implement that this year. Will and Andreas, who are both laughing maniacally having gone through this and survived it in years past. There's a reason why they're on the call. You'll see in just a second. They know what you've all been through, and they're laughing at your facial expressions, understanding your pain, not laughing at you, laughing with you. You'll laugh in the future. The continuation passing style transformation. You go ahead if you want to say something, Andreas. Feel free to hop in here, or Will, you can say something.
Yeah, well. I'm just saying, clearly they're just so understimulated by doing this course, Frank. You don't you're too soft on everyone,
So you've seen the continuation passing style transformation, although you didn't have to implement it, you had to deal with it. That's pretty cool. You've even seen the Y Combinator. Will and Andreas didn't have to see the CPS transformation or the Y Combinator, but they did have to implement the compiler. And we've, homework number 7, because I'm such a kind soul, didn't happen. So that means that you didn't actually implement amortized inference, meta learning, and/or one of the RL objectives / problems. But I think it would be relatively straightforward for you to do so, given what you now know. So there are some things you probably have picked up, but may not even realize that you've picked up at this point. Certainly some of you have learned how to program much more proficiently during this time, which is great. Again, I said at the beginning, the real point of the course is to give you perspective. I guess that's really the point of any course, is to teach you how to think in a slightly different way. But in this particular course, I don't expect you to go off and use your Hopl implementations or Fopl implementations to solve problems when you start consulting or whatever. But I do know with absolute certainty, based on experience, that you would be able to go off and use Stan or Pyro or whatever very proficiently now. There's no question that you will understand what's going on and be able to pick up those languages instantaneously, more or less, right? You certainly have gotten to the point where you can read and quickly digest papers in in this research area, which is part of the point of this. So you definitely can read inference papers now, deep generative modeling papers, shouldn't be an issue, so on and so forth. More to the point, and these last two, I think, take a long time to sink in, and we don't directly address them. We hope that they come along with the rest of the baggage in the course. It should be relatively apparent to you how to frame optimization problems as inference, and certainly how to frame inference problems as optimization. They go hand in hand. And that extra degree of freedom in how you think about framing problems will end up being beneficial to you regardless of whether or not you end up doing inference or whatever in the future. And the last one is the hardest one to get across without actually making you solve problems using the systems that you've designed and built. But thinking generatively is just a whole different way of thinking. And we've advocated for that and talked about it basically throughout the term. So the good thing for you all is that from me, that is going to be it for the term. So congratulations for surviving me. I appreciate your time and attention. I appreciate the amount of effort that you've put in. And I know, even if you're not certain of it right now, that what you've gotten out of this will be extremely valuable in the future. So thank you very much. The really awesome thing is that the two lovely gentlemen who have appeared out of thin air in this lecture, Will and Andreas, have kindly, well, they've been honored really with the opportunity to teach, which I don't let my students do very often because I want them to be research productive maximally. But these guys did such a good job of putting together the lecture materials that I asked them to come in and actually give the lectures on the material that they prepared. So we'll be giving a lecture on Thursday on normalizing flows and sort of probably recovering in the beginning of it reparameterization. And then next Tuesday on the very last lecture of the course, Andreas will be talking about generative adversarial networks and adversarially learned inference, which is basically another view on all of the activities that we've been undertaking throughout the entire course, but using models that do not have evaluable likelihoods. So, and I should say, if you look at the lecture notes that they have prepared, I think you'll be in for a treat. And I expect to see, and participation points will be duly added or subtracted whether or not you show up. You should show up to their lectures. So please do. They're going to be very, very good. They know this stuff way better than I do. So that's it. Thank you. Questions, comments? Nothing like a round of applause with people's microphones turned off. Thank you very much. If there are questions or comments, I'll stay around for a little bit, but I'll turn off the recording now.